My name is Gopi Krishna. Today I discuss about the introduction of hashing and separate chaining. Hashing is a technique used to store and retrieve data quickly. Instead of searching through a linked list linearly, we use a mathematical function called a hash function to directly compute where key should go to in a table. This gives us constant time access, identically order of one time. A real life example is a student record system. Instead of searching every student's name, we should compute a roll number using their ID and directly access their record from a table. This is what hashing tries to replicate: fast, efficient, and lookup. A hash function takes a key like a number or string and maps it to a specific index in an array called a hash table. The function we often use is a simple modulo operation. Index equal to key modulo table size. This means if we have a table of size 7 and our key is 15, the hash index should be 15 modulo 7 equal to 1. So we store it is at index 1. This is fast and works well for evenly distributed data. The hash tables are just arrays, but the trick is we use the hash function to jump directly to the spot we want. What is collision? Here sometimes two different keys give the same index. This is called a collision. For example, key of 1 equal to 14, key of 2 equal to 21, key of 3 equal to 28. All of them will have to index 0. If our table size is 7, 14 modulo of 7 equal to 0, 21 modulo of 7 equal to 0, 28 7 equal to 0. They can't all fit into the same slot, so we need to handle this situation. Collisions are unbelievable because the number of possible keys is usually much longer than the table size. The key is how we resolve them. What is separate chaining? One of the most popular way to handle collision is a separate chaining. Here how it works. Instead of storing a single element at each index, we allow each index to point to a linked list. So multiple keys map to the same index. We just add them to the list at the spot. For example, keys equal to 100, 105, 200, 205. H of k equal to k modulo 10. Hash values: h of 100 equal to 0, h of 105 equal to 5, h of 200 equal to 0, h of 205 equal to 5. Here in the array 0 position 100 and 200 are spotted, and in the fifth position 105 and 205 is stored. Each index is the hash table points to a linked list. If we multiply keys hash to the same index, they are added to the list. Formula: h of key equal to key modulo table size. So we discuss about the C code. Inserting using separate chaining. Look at how we implement in the C. Hashtag define table size. We define the size of the hash table. Struct node int key struct node next. This defines the linked list node. Each node stores the key and a pointer to the next node. Struct node table size. This is the hash table itself. It is an array of pointers to node. Each element will either be null or point to the head of a linked list. Here how the insertion function works. Void insert int key int index equal to key of table size. First we use the modulo operation to find out the index where the key should go. Struct node new node equal to mloc size of struct node. New node of key equal to key. New node of next equal to null. Then we create a new node and store the key in it. Now we check if the index is empty. If table of index equal to null, table of index equal to new node. Else if it is empty, we place the new node there. But if there is already a node, we traverse the linked list and add our new node at the end. Struct node temp equal to table of index, while temp next of temp equal to temp next equal to new node. This keeps all keys at the same index in a proper chain and insertion remains efficient. Time and space complexity. First we discuss about the time complexity. Let's talk about performance. In the average case, the table will be well sized and the hash function is good. We only have a few elements per chain, so search, insert and delete and take order of 1 plus x times, where alpha is a load factor or x is a load factor. In the worst case, where all the keys collide to the same index, each chain becomes long and operations take order of n time. Space complexity is higher than the simple arrays because we store extra pointers in the linked list. Advantages: easy to implement and understand. Deletion is simple, just remove a node from the list. No cursor rating like a linear programming. No upper limit on the number of keys per index. Handles collisions efficiently, easier and deletion than probing methods. Comparing to linear probability, no cursor trading uses extra space like linked list. Disadvantages: use more memory for pointers in the linked list. Performance drops if chains get long. Depends on the quality of the hash function. Per searching in long chains take more time. Order of n, worst case if all the keys will collide. Requires extra memory for pointers like linked list nodes. In real world applications, separate chaining is used in many systems. Java's MashMap older version, Python detections before version 3.6, compiler symbol tables. Conclusion: to sum up, separate chaining is a reliable and flexible method for handling hash collisions. It is easy to implement and works well in many real-life situations, easily when data is constantly being added and removed. Understand this technique help us build more efficient, scalable data storage systems.